Our first presenter is Julian Anthony. Julian's an NX developer with Maya HTT. He has 2.5 years of experience working in the structures team at Maya, developing the Siemens NX correlation and NX open tools. For the past year, he's been working in combining AI with NX correlation products. And his topic today is real-time stress prediction using machine learning. So over to you, Julian.
Thanks, Todd. Okay. With the increasing availability of various devices for sensing and reporting information of all kinds, customers are developing a digital twin approach to predict failure of their equipment in real time. A digital twin is an analytical model of a structure which can be queried using IoT data to determine the behavior of a real-world structure. With the data gathered about structures in service, this information can be used to increase the effectiveness of these structures or allow their use to be better monitored. For example, this information could be used to monitor the remaining useful life of structures with limited lifespans so they can be maintained more effectively, thus reducing their downtime and their total cost of ownership. Preliminary studies in various domains, such as turbomachinery, have already shown that large cost savings are possible if the remaining life of engine components can be predicted in real time. For example, the life cycle cost savings of high-pressure spool discs can range from 1 to 1.4 million Canadian dollars if the 25K hours overhaul requirement can be doubled. Given the large number of turbines sold every year, this could translate into significant savings. Unfortunately, the instrumentation allowed by these new IoT technologies is rarely enough to ensure complete coverage of the interesting part of a structure. Therefore, in order to build an effective digital twin for failure prediction, we must be able to predict stresses at high interest locations, which may not be instrumented themselves. In addition, the digital twin must closely model the behavior of the real structure and must be able to return results quickly when fed new measured values. Finite element models of complex structures can have problems with both of these, often taking too long to compute and return results. So here we examine the possibility of using results from finite element modal analysis to train a neural network to predict stresses at various locations based on known accelerations at others. It is more logical to train a neural network using simulation data instead of in-service data, given that a large number of data points can be readily generated and we can control the test envelope. If this can be done successfully, then accelerometers can be placed at convenient or accessible locations in the real-world structure, and the data from these can be used to predict in near real-time stresses at other more interesting locations. In many cases, a limited amount of data can be obtained from test articles or a limited number of extensively instrumented structures. This opens the door to using the concept of transfer learning in order to use this limited amount of real-world data to tune a neural network trained from a finite element model to better reflect the behavior of the real structure. This study examines the feasibility of this approach with a very simple structure. So this approach would require a lot of training data. However, with the aid of tools developed at Maya, this was achieved very efficiently. We start with NX Nastran to perform a normal modes analysis and then carry random base excitation simulations using Maya Structural Analysis Toolkit, also known as SA Toolkit. A model of the bike frame was used to demonstrate this experiment. This model was clamped at the bottom bracket as displayed here. Normal modes analysis using the Lanczos scheme was performed to determine the top 10 modes of the system, and it was found that the frequency range of the normal modes range between 40 and 364 Hertz. So using the normal modes analysis, 30 locations for acceleration and 30 locations for stresses were determined. Subsequently, the system is subject to random base excitations at each of the enforced motion locations in each degree of freedom. The random base excitation is an acceleration PST between 1 g and 10 g's in the range of 50 to 350 hertz. Peak von Mises stresses and accelerations are thereby extracted for each simulation. This served as the dataset used to train the base neural network, and in order to train the network, 27,000 of such simulations were performed. So the first step of this project involved building a base neural network. For this, the popular machine learning library Keras was used. Once a neural network was configured, the next step was to fit the simulation data and thereby train the neural network. The data was split into training and testing datasets randomly, using an 80-20 split to ensure the distribution of data in both datasets were as similar as possible. We used the Adam optimizer to solve this regression problem. The objective was to minimize the loss function, which was the mean squared error, and also track the evolution of the mean absolute error, as this is a more convenient way of describing the accuracy of the trained neural network. In order to find the best neural network configuration for our problem, we explored the hyperparameter space by altering 3 hyperparameters. The learning rates were changed from 0.1 to 0.0001. The number of hidden layers were altered from 1 to 4, and the number of units per hidden layer was changed from 5 to 50. Taking a typical neural network layout, the input layer is shown in blue, hidden layer in purple, and output layer in red. We vary the number of hidden layers of the neural network by adding more layers, as shown here. And we also vary the number of units in the hidden layers by adding more units, as shown here. Exploration step produced 192 different neural network configurations. Each block in this plot represents different combinations of hidden layers and units per layer for particular learning rates. The first 48 are not shown here, and the high learning rate of 0.1 was used, which didn't allow the optimizer to converge. These different neural network configurations were trained using data from the base model, and the mean absolute errors were evaluated. You can see that as the learning rate decreases, the general trend is that mean absolute errors decrease. However, the change from a learning rate of 0.001 to 0.0001 wasn't much, and so we'll focus on this middle block for now. A general trend of increase in number of units per layer leads to a decline in the mean absolute error can be observed. Next, as the number of hidden layers increase, the mean absolute errors drops even further. However, this is observed up to a point before which the improvement isn't significant. The goal of this analysis is to find a neural network configuration that is simple but has reasonable accuracy. This criteria was met by the combination 330 and hence was chosen. The slide shows the convergence of the chosen configuration. The configuration was trained for 100 epochs, and as you can see, 100 epochs was enough to achieve a good convergence for the mean squared error. Step 2 of our project was to tune the base neural network developed in step 1 via transfer learning to predict stresses from accelerations on the same byte geometry but with different physical properties. We applied 3 different transfer learning techniques, which 1, used the base neural network as a weight initialization scheme, 2, froze initial layers, and 3, added extra layers. Similar to step 1, we explored the hyperparameter space to find the best neural network configuration for the adjusted model. To perform transfer learning, we tweaked the material properties of the base model to produce a second model called the adjusted model. The thickness of certain components of the structure would drop by 5% of the stiffness, and the stiffnesses were raised by 5%. A shift in modal frequencies was observed, and as a result, another 27,000 training examples were generated. But only 1,000 examples were used for the tuning or transfer learning process. Given a maze model as shown here, transfer learning can be applied as follows. We can freeze an initial layer, This means the weights associated to the frozen layers are untrainable and therefore fixed. Only the latter layers are trainable. Then we can add extra hidden layers. Next, we can add units to these extra hidden layers. Translearning exploration step produced 48 configurations. This plot consists of 4 sections indicating how many layers were frozen. Each section displays the mean absolute error for varying combinations of added layers and added units to these layers. The first number at each point represents the number of added layers, and the second number represents the number of units per added layer. For example, 245 characterizes a neural network configuration with 2 added layers and 45 units per added layer. Note that no units are added to the fixed layers. When more layers are fixed, a higher error is observed. This makes sense, as more fixed layers means less parameters are trained and therefore would take longer for the training process to converge. For now, we'll focus on the cases with no or one fixed layer. Adding a layer and increasing the units in the new layer tends to improve the error. This trend can be seen up to a point beyond which the mean absolute error plateaus off. 3 configurations were chosen as these represent the different schemes that were tried. Chosen configuration 1, the base neural network was used to initialize the weights, and therefore all parameters were trainable. Chosen configuration 2, the weights of the first layer of the base neural network were fixed, while the rest of the layer's weights were trainable. Chosen configuration 3, the weight of the first layer of the base neural network was fixed, a new layer of 35 units was added, and all the latter layers were trainable. This proved to be the best configuration. The last experiment conducted was to investigate the effectiveness of using transfer learning. For this part, the mean absolute error and the time to train/tune were computed for the following cases. Using the base neural network to predict adjusted stresses, therefore no transfer learning, training a neural network using only adjusted data and use it to predict adjusted stresses. But here again, there's no transfer learning involved. And finally, tuning the base neural network to obtain an adjusted neural network and using it to predict adjusted stresses. Here, there's transfer learning was involved. So case 1 resulted in high training and testing mean absolute errors. This makes sense as the base neural network was trained on data points from the base model, but is being used to predict stresses from the adjusted model. Case 2 took only 10 seconds to train due to the low number of data points used. Only the 1,000 adjusted model cases were used. This also resulted in better training and testing mean absolute errors. For the final case, a learning rate of 0.0001 over 500 epochs was used to tune the neural network. The smaller learning rate over a higher number of epochs took around 45 seconds to tune the neural network, but resulted in the best training and testing mean absolute errors. Due to the large number of base model cases used to train the initial base neural network, the base neural network proved to capture the physics of the base model very well. Through transfer learning, with only a few cases of the adjusted model, this knowledge was effectively transferred to capture the physics of the adjusted model successfully. To conclude, in step 1, we trained a base neural network. Here we generated 27,000 simulation data points of accelerations versus stresses. We explored a hyperparameter space involving 3 hyperparameters, and we successfully produced a stress predictor from bike frame accelerations. In step 2, we tuned the base neural network via transfer learning. We used 1,000 simulation data points to tune the base neural network to predict stresses on a bike frame with different physical properties. And we applied various transfer learning techniques to achieve a better mean absolute error in comparison to training a neural network from scratch. Improvements and possible applications. We could extend the study such that stresses at any location can be computed given accelerations from any location. It would be useful to couple this neural network to a system to make real-time live predictions, prepare overhaul schedules, and detect anomalies. And finally, the successful use of transfer learning demonstrates that this approach could be done using test data from a certification unit, whether it be a turbine, an aircraft, or an automobile, and then extended to any subsequent units. This brings me to the end of my presentation. Thank you very much for listening. If you have any questions, I would be happy to answer.
Okay, thank you very much, Julian. That was a really great presentation. We do have a few minutes for questions, so please use the question mark at the top of your window. And we do have questions coming in, so we'll go ahead and start with those. The first one, they made a comment, the results look great. And the question is, are you ensuring that the random simulated accelerations loads to generate the training data corresponds well with the actual realistic accelerations?
So this was just sort of done as a proof of concept. So we haven't really checked what the actual accelerations would look like. But a good next step for this would be to use very similar accelerations to real life data.
Okay, thank you. Any other questions? Please add them to the chat. Another question is, would this technique be applicable to other kind of engineering analysis, such as fatigue, fracture, and VH?
It wasn't tried with other sort of engineering principles, but I would think so. Yes.
Okay. So with the transfer learning, how do you quantify uncertainty?
So one other thing we did consider doing, but we didn't get to do this analysis, was to so instead of the mean absolute error, which is sort of taking an average of all the errors in a training or testing data set, it would have been interesting to see how the individual errors would be would compare to sorry, how about I say this? It would be interesting to see how the individual errors would compare within within each test data point. This was something that we hadn't tested out, but it would also be a good next step to try.
Okay. I think one more question. So you mentioned near the beginning the total cost of ownership. I was curious, now that you've completed or achieved good results with the first analysis, what are your kind of ideas for applying this to real world situations? Do you see this on cars or planes or things like that?
Yeah, so I had included one in my, yeah, so like the second point here, I think a really good next step would be to try and couple this neural network, to couple this AI model so that we could do real-time live predictions and use that to, which can also be added to a system where overhaul schedules could be prepared and anomalies could be detected. So that would be one real life application that could be would be interesting to look at.
Great. Yeah, I could see this on, airplanes, for example, just to kind of areas where it's difficult to inspect or areas that we suspect that there may be problems, but it's hard to see it or feel it in when you're in flight or between flights. So this could be maybe a good early warning kind of a system for safety.
Definitely, and if specific, especially if these areas are inaccessible, but there are other locations where we could access data from or instrument better, it could be useful to we would be able to make such calculations as well.